Hello everyone, my name is Gustavo Lahr. I am a PhD student at University of São Paulo and I would like to present to you my paper with my all other co-authors named Genetic Approach for Couple Dynamics Optimization in a Multiple Degree of Freedom System. And what I mean by multiple degree of freedom is a robot, right? So that's the kind of research we're interested here in our lab. Mainly, we know nowadays that contact is very useful and very rich. Applications are done with contact, like assemblies in all kinds, fittings, rehab, exoskeletons, all kind of stuff are done nowadays with contact. So we are interested in enhancing and improving this kind of setup and doing in a way that we could improve over time also. So, so how difficult it is to improve that? Well, it depends a lot on the application. So, for example, right now we have this research going on with manufacturing for aircrafts, which is kind of difficult because it is not a scenario where robots are used to be put in. So that we have a lot of automation going on that way. We have this kind of all difficulty in reachability and confined spaces, and we also don't have the assembly line as we know, and for example, in automobile industry. So right here we need to position our robot, and that brings a lot of problems, error positioning, and all this kind of mapping localization. But also we have different shapes and different sizes, which usually leads us to different also stiffness, for example, in the environments. And contact, as I will comment in the next couple of slides, it depends on the environment. So if we have here an environment that changes a lot that our robot needs to do, so we need to focus on adapting our robot to that. Especially when we think that it's not only about having like powerful robots. We have this a lot of automation from KUKA and Boeing, but we need to think about other smaller applications, smaller planes, confined spaces, smaller where like humans are more have this tendency of accomplishing the task. So it is quite a challenge, and we need to keep focus on that. Although we cannot solve the whole problem, we are focusing on that. So how can we make this assembly with an industrial robot in a very flexible and very change like with a lot of changing environment? So that's what we're going to present here. So the technique that is broadly used to deal with contact in industrial robots is called impedance control, which is used to be called force control, but force control is kind of narrowed down to specific applications. So in a more modern term, we would like to call it interaction controllers because you need to relate how the robot will respond to interactions. So here's our kind of our setup. We have this assembly peg and hole setup, and we would like to uh, use impedance control, which here's the formula, like the kind of the control law, where the force here is the input, and M, B, and K are the controller matrices, which are used to deal with position, velocity, and accelerations during contact. And this kind of regulation between force and position, it's called impedance control. To be more specific, we are doing admittance control because we are using force, which is effort, as input, and position, like displacement, as output, which is a flow. But anyway, we kind of want to do the 3 degrees of freedom here. Like we have our plane here, which is z going down, x and y on the surface here. So we're defining a controller here, and due to natural constraints of the task, we could like make a controller on y-axis and x-axis and y-axis, but due to natural constraints of the task, the stiffness is quite similar in both directions. We can make this a resulting controller, which gives us, instead of 9 parameters, 3 for z, 3 for x, and 3 for y, we end up with 6, and I'll talk about that later on optimization. So impedance controller, it's very good for fine local adjustment. What I mean is, since the robot's quite close to the part with vision and then all kind of sensing, we can start assembling, but it needs to be fine, which means that needs correct displacement, correct positioning errors. So the performance, since if we imagine that we already guarantee stability, which is crucial to this kind of applications and all sorts of applications, uh, the performance depends on mainly on the robot and its dynamics. When I mean robot, I mean all the robotic arm, but also the tools that are being used, and also the environment. So I cannot guarantee from the robot point of view that my performance will be good enough, because I depend on the environment. I depend if the environment is stiff or kind of more soft. It depends on and when I was talking about the aircraft, we remember that different dimensions and different stiffness, and then that changes a lot. So if we can guarantee stability, how can we improve performance for the impedance control in this kind of tests? So the first main application is to use adaptive controllers, usually estimating the stiffness and damping of the environment. But the problem with these tasks is that it depends a lot on our initial guess, otherwise we will end on local optima and local minimum or local maxima, and that depends a lot from our application. I mean, it may be the best local one. So maybe that's not. If we want even better performance, we need to broaden our search space. Other way would be like, okay, let's make it simulation and make it and improve on that, learn on that, and improve our impedance control there. But the problem is usually they are 1 degree of freedom, maximum 2 degree of freedom, and we cannot put all the nonlinearities on the model. So for example, most of the papers usually deal with constrained motion. So the robot is already touching the environment, but that's not what we want to optimize, because that's not close to a real simulation, real application. So we want to be ready for unconstrained to constrained motion. That changes a lot, as it has been shown, especially in our last paper, sitting on the current paper. And the third most known way to do that, kind of, I mean, otherwise trying to avoid simulation and adaptive control, it's applying evolutionary techniques such as genetic algorithms, which is our case, or PSO, or other kind of evolutionary based optimization. These are good because they need to, we can avoid every kind of unknown parameters. Like we don't need to know the environmental parameters, we don't need to know the tools, the robots. We just need to collect data and optimize there. The problem is we need to due to this kind of situation, we need to lot of data. We need to recurrently get data, optimize, and try again, and so on. So we need to, as it's the way it is possible, we need to make it smaller, make the search space smaller, or stop early. I mean, we need to have less parameters to optimize. That way we can have a faster convergence. So that's kind of a gift from genetic approach. So our approach in this paper is let's make genetic-based optimization, which we will work with on the hardware in the loop setup. So for each trial, for each loop on the optimization, we run a physical experiment, feedback all the signals read, we extract the the metrics and go back to the optimization, and this keep going until we reach our stopping criteria or the maximum number of evolutions. So we still go from this unconstrained to constrained, which is more realistic. It's already on the parts, already on assembly situation, so it's very close to what is supposed to be on industry in this kind of applications. One thing it's important to remember here, it's decoupled, so I can optimize Z, but look for different parameters in X and Y, although the task is not. So thinking about that, we reduce the search space, as I talked earlier, and we go from this 9 parameters to 6, and we optimize in a stable parameter sets. So we minimize total variation, settling time, error of steady state in X, Y direction, which is the equivalent of X and Y, but combined, and in Z, trying to optimize all the parameters of the stiffness and damping and inertia matrices. Here are our constraints in number. So the optimization statement here, it depends on, I'll go very quickly here with the metrics we're using. So we have these two metrics which are a trade-off. The first one is the settling time, where we get in the envelope, and after it never gets out of that envelope, that's the settling time. And the steady state is the error between the black dotted line and the signal here. So for this example, it's almost very close to 0. And the last one is called total variation. So if we have like all the valley and peaks of our problem, and we get, keep getting the delta, the difference between a valley and a peak, consecutive ones, and we sum all of these, that's called total variation. And total variation measures the amount of vibration, oscillations on our system, while the settling time, it needs to be smaller because we need to finish as quick as we can our assembly. So all the metrics for Z are the way they are here, and for X and Y we just take the module of in that plane, the XY plane. So the genetic algorithm goes to, we use the NSGA3, which is a more recent version of the NSGA2, which is very common genetic algorithm. So it goes like, it makes a first guess, then we try that guess, and then the algorithm proposes a lot of other ones, and then we try all of them, get all the data, and then feed back to the genetic algorithm. So in our system here, we propose 20 different ones, and then there's another loop, and then measuring again, and we use it here at 20 generation setup. That's more than enough to our system here, as we will see. So here, the experiment is, we want to, we get closer, we know the right position, but then the algorithm, inserts a random error, and then we start the experiment. So the random error with the hardware in the loop setup gives us a very broad configuration application. So that's really important to us. So we have this amount of time that the algorithm, that experiment can run, and then when it's settled, we get all the forces related to that experiment. We don't get track of the error, so it can change a lot for different parameters. And then when it's done, it just restarts, goes up and restarts with different error, as in we will see right now. So that's the main experiment. So we get for the first generation here, we have a lot of oscillations in Z, sorry, and then we have, can you see here also all positive as because it's the norm for X and Y. And after the 20th generation, each signal here, as in the first, is a different MB or K, different impedance controller setups, a different trial. So we can see that oscillations got much smaller, and also our system got quite fast to converge here for some. Other ones, they have, as the genetic algorithm tries to get all the Pareto front, we can see here that we have very good candidates for what we are looking for, which is very small oscillations and very quick settling time. So just a quick show. This one here is the best individuals being recorded. This is the same recording I showed you earlier. The second one here in the corner, it's the worst. So as we will see, when it goes try to achieve, we can see oscillation in the tool. Some authors would categorize this as unstable, as we're talking about interaction control. So although it's not, classic instability, is just, it's bouncing, and that's not a good setup we want. We don't want that. So we got the Pareto front. The Pareto front here, as we have three different parameters. We got like these two. We plot plane by plane. So total variation and error. We can see here the black crosses. That this is the first generation of random impedance control parameters, and the red one here, it's the last one. As we can see, we actually got a Pareto front here with minimizing the steady state error. So the algorithm tries to get like all this distribution across total variation here. So we don't forget that we have the couplet Z and XY. So we can see here for the same metrics, total variation and error for the Z. We can see the Pareto front here. That's the same between steady state error and settling time. We can see in the red dots here, you can see the front being formed. But when we plot total variation settling time, as we can see, we don't have like this clear Pareto front. That's because they are very trade-off variables. So we need to take care of all that. In conclusion, then, we implemented a genetic algorithm that was capable to optimize in a very real, very close to real scenario, industrial scenario, with displacements and forces, interaction controllers, industrial robot, and it didn't take like the whole day to optimize. As we can see, you can read on the paper that we can, work on a stopping criteria to stop early. But we can have like something like 6 generations, like an hour or something. We get like the optimal things. So reduction of search space was really important here because it took us much less time. And it's really robust to positional error because, as we can see, the error was random and still could get the parameters that were, so they are converged. So as future work, we would like to work in a stopping criteria, which is really important, and also to bring the rotational axis on the optimization, which will bring us to even more optimization parameters that we need to work on, but that is just part of the problem. So we would like to thank all the partners and people involved, all of my colleagues, and I hope you have the best conference. Stay safe. Best regards.